Hello students, in this lecture we are going to study the convergence and completeness, our third article of this unit. Now convergence, what do you mean by convergence? In second year we have studied the real analysis first bit in the semester third. So we have seen Cauchy sequence. Cauchy sequence means that is mod Sm minus Sn less than epsilon, then that the same concept is here. But here the space, we are changing the space only. Here space is the metric space. Here in place of mod we have to take the D, that is the metric on that set. So let xd be any metric space. Then the sequence an of points capital X is said to converge to a point small e of capital X if for each epsilon greater than 0 there exists a positive integer m such that d of an a less than epsilon for all n greater than or equal to m. D of n in place of mod, that is d of an a tends to 0 as n tends to infinity. So this is the definition of convergence. In every theorem we have to use this definition. So d of an a less than epsilon for all n greater than or equal to m, or we can say that d of an a tends to 0 as n tends to infinity. Now we can also convert this definition in terms of open sphere. We can also write this definition in terms of open sphere, that is for each open sphere S epsilon of E centered at E, there exists a positive integer m. There exists a positive integer m such that an belongs to S epsilon of E. Now an belongs to S epsilon of A means what? Distance between A and A. We know the definition, that is the open sphere. What is open sphere? That is SR of X. What is this definition? X such that, or SR of A I say, X such that this distance of XA that is less than that R, that is SR of A. This is the definition. So here this an belongs to S epsilon of X. Just this is the conversion of the definition in terms of open sphere. Now let us see what is meant by Cauchy sequence. What is meant by? One thing I have to mention here. Suppose this is the sequence an and suppose converges to A. So we can say that this we can write like this. Just take arrow. Its meaning is this an converges to A, or we can say that limit an n tends to infinity is equal to E. Its meaning are same, both these three statements. An converges to A or an tends to A, we can say that, or this limit an n tends to infinity is equal to E. So we must know these things for our future theorems. So now let us see the definition of Cauchy sequence. So a sequence an of points of capital X, of course let xd be a metric space, and this an sequence of points of capital X is said to be Cauchy sequence. Is said to be a Cauchy sequence if for each epsilon greater than 0 there exists a positive integer n0. There exists a positive integer n0 such that distance of x and xm it is less than epsilon, and for all n greater than or equal to n0. In the last year we have seen this definition and we have written that mod xm minus xn less than c. You can see your notes of second year. Mod xm minus xn less than c. So here we are considering the metric. So therefore this d of xn xm, it is less than epsilon, and for all ln greater than or equal to n0. So this is the Cauchy sequence. Cauchy sequence. Or in other words, we can say that this is a d of xn xm less than epsilon, or this d of xn xm is tends to 0 as this mn tends to infinity. This also we can write. Now there is one theorem that is important theorem. So prove that every convergent sequence is a Cauchy sequence. Prove that this is the theorem. Prove that every convergent sequence is a Cauchy sequence. In the last year also we have seen this theorem, but at that time we have considered just only set of real numbers. So here we are considering the metric space. So here how we prove this? Let xd be any metric space. Now we have to consider one sequence. So let this curly bracket in A and B sequence of points in capital X converge to small a. This we are supposing. So suppose that this converges. Now convergence means today we have seen the definition of that convergence. So from that definition, as this equals a, this converges to a. Therefore, for epsilon greater than 0, there exists a positive integer. For epsilon greater than 0, there exists a positive integer such that d of a and a is less than epsilon by 2 for all n greater than or equal to n0. For all n greater than or equal to n0. Now we can write d of a and am. D of a and am, that we can write d of less than or equal to d of a and a plus d of a am. How we have written? Last year we have made some like this. See, am minus an. You can write this. That is, or am minus. We can write this am minus a plus a minus an, and by that triangular inability we can make this calculation. So just like that, this d of a and a plus d of am. Now here we have written d of a and a less than epsilon for all n greater than or equal to n0. So here it is less than epsilon by 2. It is less than epsilon by 2, and which is equal to epsilon. And therefore this d of a and am is less than epsilon for all m n is greater than or equal to n0. So here it is a Cauchy sequence. And therefore it is proved that every convergent sequence is a Cauchy sequence. Now one thing I have to mention here, its converse is not true. Of course, every convergent sequence is a Cauchy sequence, but it is not true that every Cauchy sequence is convergent. And if every Cauchy sequence is convergent, then that is said to be the complete. This is the article, that is the convergence and completeness. Now what is complete? Complete means in our mathematics. Complete means not whole. In our mathematics, complete means every Cauchy sequence is convergent. This concept is called as completeness. And its converse is not true. So these two things we will see in the next video lecture.